All right, welcome everybody. I'm Professor Sam Burden here in the Department of Electrical and Computer Engineering, and it's my pleasure to be hosting our colloquium speaker today, Professor David Remy. So David's currently a full professor in the Institute for Nonlinear Mechanics at University of Stuttgart in Germany. It's actually where he did his undergraduate work, so it's kind of a cool return home or full circle for him. But in the meantime, he got a master's degree in mechanical engineering at University of Wisconsin, so the other UW, the one that's east of the Mississippi or closer to that. And then he did his PhD at ETH Zurich with Roland Siegfart before going to University of Michigan to be an assistant professor. And then he got tenure there. He received the NSF Career Award, and then he moved back to his current position. So David works on a variety of really cool stuff. I think today the focus is going to be on his work on robotic locomotion, but he's also worked on rehabilitation, assistive devices, human in the loop optimization, novel actuators, just a really wide variety of things. But I think focus today, based on the talk or the title in the abstract, is going to be his work on legged locomotion. So thanks very much for taking the time, David. Please take it away.
Thank you. Right. So if you did the calculation, that's 4 transatlantic flights. I don't know if this is going to be possible in the future when we all have to save the climate. Well, thanks for this nice introduction. Thanks for having me here on your wonderful morning, my wonderful evening. Thanks for the introduction. It is true, I do work in a range of different topics. And here's a quick summary, right? So I do work on legged robotics, actually building, designing robots, implementing them, writing controllers, getting them to walk. So this is Starlet, basically my PhD work. And then we, at Michigan, we have this biped RAM1, and then this is RAM-B. That robot is currently with me in Stuttgart. So actually a lot of hands-on work of getting stuff to walk, to run. I do work in the field of soft robotics. You see this later in the talk. All the robots that I build, they have springs somewhere, and that got me excited about soft systems in general. Trying to build continuously deformable systems. At this point, they're all sort of this manipulator type of soft robot, but we're trying to not do sort of this explorative work that is happening a lot in the field of soft robotics, but instead doing more mathematical modeling control with these systems. And sort of my goal is to, at some point, actually build legged robots from soft material. But I think when we want to get to that point, we first have to basically understand them much better. And these very simple manipulator systems are better suited for that task. The third area is rehabilitation robotics. Sam briefly mentioned it. One of the biggest contribution that we have there was this idea of body in the loop optimization, where a assistive robotic device is controlled by some controller that needs to be tuned or parameterized on a subject-specific basis. And what we're trying to do is to measure some physiological cost function, for example, energetic cost, and use that to drive an actual online numerical optimization that finds optimal parameters in real time. That idea has really taken off, and we're still working on it. So I still have a student in Michigan who is working on this part, right? Fusing different sensors, estimating energy cost in real time, trying different tricks to get better sensor values, because the biggest challenge in this, right? This looks really simple as a diagram, but the data that you get here is very, very noisy, delayed, has all sorts of issues. So there's a lot to be gained if we can get that process to work a little bit better. And I understand that one of the topics of the seminar series is human in the loop control. So this would be a wonderful talk for today. I'm not going to do that. Instead, I want to talk about my last area of research, which I call the locomotion principles or fundamentals of locomotion, where we're using engineering tools, mostly simple models, to understand how locomotion works in nature. Not so much to help biologists, even though that happens once in a while, but more because we want to extract fundamental principles that we then can use to build better legged robots, better assistive devices. And that's what I want to talk about today. And a big part of my motivation for that area comes from the existence of different gaits. If you look at nature, you see animals and humans moving in very, very different ways, right? There's a lot of variety out there. But then if you look closely, there's also a lot of structure. Like quadrupeds tend to use a walking gait if they move at slow speeds, mostly independent of the species, right? At intermediate speeds, we have trotting and pacing, and then at high speeds, you get galloping gait. So it's not completely random. So if there's structure behind this variety, and we are trying to understand where gaits come from, and sort of with the end to understand how we can use gaits to make legged robots more efficient, faster, more agile. And our tool of choice, as I said before, are simple models. Here you see a first set of such models. They all have different number of legs and different morphology, all planar. So in a sense, they're very conceptual, but they do model real properties in the sense that they have distributed mass, they have damping in the springs, they have actuators which have limits, and so on and so forth. And they are all driven by series elastic actuation. That means my motor is typically sitting here on the top of the spring, is compressing the spring, and in that way creates an action or force acting along the leg or acting along the hip. And in between, you have springs to create sort of a passive dynamic behavior. And we do that because that's what we see in nature. If you look at a horse leg, it can be approximated almost perfectly by a linear prismatic spring. And because the robots that we build also use that actuation scheme of series elastic actuation. So very conceptual generic models that do represent essentially a large class of robotic systems. And what we've done with these systems was that we were trying to find the most optimal, most energetically efficient ways of moving by using large-scale numerical optimization. So we basically took a step back and asked ourselves, what is legged locomotion? What is, in a sense, a gait? Well, it boils down to just two requirements. A, you want to move forward. You want to get somewhere. And then B, we request or require this motion to be periodic. That's not strictly necessary, but it makes the problem a bit easier because if you have a periodic motion, you can repeat it over and over again, and you will get continuous motion out of that. Then, of course, you have to obey the laws of physics, the rigid body dynamics that are behind such a mechanical system. You have to clear the ground. Your actuators have limits with regard to speed and maximum actuator force. And all that we combine into a set of constraints. And then we solve a optimization problem with some cost function, for example, the amount of simulated electrical energy that this robot is using to locomote. And all that gets thrown into the computer. The computer systematically tries different motions, and this is what it comes up with. For biped, at slow speeds, the robot should walk in sort of every sense that a biologist would classify walking. So we have, this is a contact pattern. So you see when feet are on the ground, and you see here that there's a double support phase. So you have a double stance phase that's also typical of human walking. And then if you look over here, those are the vertical ground reaction forces. And they also show what is very typical of walking, also observed in humans, this double hump profile where there's a mid-stance relief. That's when the spring gets extended a little bit and the contact forces actually go down and then they rise again until you leave the ground with the foot. And then, of course, the contact forces are 0. That's what you see at slow speeds. If you increase the speed, you see running. Again, all the characteristics are there. There's an air phase, so sometime where both feet are in the air, where they exceed no forces on the ground. And when they're on the ground, they show this single hump ground reaction profile that is typical of running, for example, in humans. We did the same with quadrupeds, looking for optimal locomotion there. And we found that walking, trotting, and galloping are the most efficient gaits, similar to what we see with animals in nature. Galloping only got the most efficient gaits when we added a flexible spine. So we extended our model to make it a little bit more realistic. And it's kind of nice to see that with these slow symmetrical gaits, walking and trotting, the spine is not really used. Those curves show the energy usage, the cost of transport as a function of speed. And we see that walking is most efficient at slow speeds, trotting at intermediate speeds, and then at the higher speed range, we see that galloping is most efficient. And you see here also that the spine, there's the solid line, really helps with these asymmetrical gaits, right? You look at the videos, that's not surprising. So those are optimal motions for a quadruped, and then we extended that to real robots or to a model of a real robot. So we carefully identified a model of our robot Ram 1. Everything was made as realistic as possible: mass distribution, spring stiffnesses, friction in the joints, damping in the springs. Our cost function was made as realistic as possible. And we played sort of the same game, found optimal motions at slow speeds, walking, knees are extended, double support phase. High speeds, we get running, knees are bent, elastic energy storage. Again, all the characteristics of running. I know that was super fast because that was just the intro. And that was also a summary of the talk that I gave at UW about 4 years ago, right, where all these results were kind of new. And we were super happy to be able to actually generate these motions through optimization alone. If you look at these results from the outside, they are trivial, almost, right? Because, I mean, what I'm telling you is that my robot should walk at slow speeds and should run at high speeds. But we do that as well, right? So why would you expect something different, right? But the truth is that all these systems are very, very different, right? You have humans, you have these conceptual models with prismatic legs, and then you have the actual robot model with articulated legs, with joint friction, with actuator effects. This is driven by muscle, this is driven by electric motors. So the structure of these systems is very, very different. Yet we end up seeing the same gaits, independent of what we have here. And to me, that's a puzzle, because this here is created by an optimizer who's completely agnostic to the world of legged locomotion, has never seen a horse, has not been primed through the choice of initial conditions to find walking or running, right? It was just picking the most optimal way of moving about for, of course, a given contact sequence. But we tried all these different contact sequences and we ended up with exactly these results. And that's basically the puzzle that is behind my presentation today, where I want to talk about sort of the hypothesis where these different gaits come from and why we do see them in all these different systems. And the hypothesis is basically that what we're seeing here are just different modes of one oscillator. If you look at the schematic here, right, I have two masses on thin beam. Something like this can oscillate, right? And it can oscillate in different modes, right? The two masses can swing towards the same side of the system, or they can swing against each other, typically associated with different frequencies, but we have these modes, oscillation modes of one oscillator. And the idea is basically that we see the same for our legged robots, which are also oscillators. They're just a little bit more complicated, right? But they have inertia, they have elastic elements, they can do pendulum motions against gravity. So they have all the ingredients that you need for an oscillator. And the idea is that they basically have some modes, right? Passive modes that occur natural in the mechanical structure. We would call these nonlinear, non-smooth normal modes, because this is, of course, a nonlinear system and we have contact. So things get a little bit more complicated, but the idea is basically the same. And then if I try to run an oscillator optimally, I typically should do this as close as possible to resonance. So this guy, I should either run at this frequency using that mode or at this frequency using that mode. And for a legged robot, well, at slow speeds, maybe I use the walking mode, and at high speed, I use the running mode. That's the basic idea that we have. And then, of course, the question is, how can you identify these non-smooth, nonlinear normal modes, or how can you find them? And the way we did it was that we took this model that was already conceptual to begin with, but made it even more simple. We removed everything that created losses. We removed the actuators. We removed things that could dissipate energy, for example, through contact. So we took the foot mass in the limit to infinitely small and essentially created a completely passive system. And since this passive system doesn't have any actuators, these modes, these nonlinear modes, would show up as periodic motions. Orbits in the state space, oscillations that exist without any input. Inspired was this by some work done prior. One is a paper that I consider really seminal by Hartmut Geyer, who discovered a very simple model that could both do running, as shown up here, and walking, as shown up here. It's not a fully dynamic model because it uses some control. It has a so-called angle of attack. So the foot, you see this in the animations, the foot immediately snaps to a certain predefined position as soon as it's in the air. So there is a bit of a controller happening there. But he was sort of the first person to find two gaits within the same model. And then Sean O'Connor at the University of Michigan also developed a nice model that uses a hip spring here to get leg swing action, and was also able to discover these two gaits. And what we did was mostly inspired by his model. Okay, how does that process work? We have our model. It has a dynamic state, so joint angles, joint velocities, that is somehow represented by a point in our state space. We define the beginning and the end of a stride by just considering a section, a Poincaré section of the state space that corresponds to the model just hitting the ground with one foot. So this defines the start of our periodic motion. There's sort of two ways you can do this, either with the second leg in the air or with the second leg on the ground. So we have to consider both. And then basically what we do is we pick just the point on that Poincaré section, pick a state, an initial state, and let the model go. And in most cases, it will just fail spectacularly. No periodic motion. the model, the robot, will just fall. If you choose your initial condition a little bit more careful, you get at least a stride, and a stride meaning that after some motion, you end up hitting the ground again with your right foot. So you're transversing this Poincaré section again. But as you see here, right, this orbit is not yet periodic. And if I keep running this motion, you see that it sort of will spiral out of control and will fall. This one actually falls really spectacular. So if you search very, very careful, you eventually find something that is periodic. So you start on the Poincaré section, you get some motion, you get a stride, contact left, and the moment you get contact right, you end up in exactly the same state again, right? That's the definition of periodicity. And then you can just keep doing that over and over again. So that is a limit cycle. That's the limit cycle that we're looking for. And the important part now of this work is that we not only want to find one periodic motion, but we want to find all of them. So there might be another one over here. This one may be corresponding to walking. This one here corresponding to running. And we assume that they're somehow connected. And of course, the question is, how do you find all of them? A tool that helps there is numerical continuation that you can imagine works the following way. If I have found one periodic solution, I can do what's called a Floquet analysis and basically disturb that solution a little bit. So instead of starting at x star, which is periodic, I add a little delta x and start over here. And I simulate my stride and I end up somewhere else, right? Not periodic. And my delta x has changed from this pink pre-stride to a green after stride disturbance. And then I can do this in all different directions. And I essentially create a local map of what's happening around my periodic solutions. And I go ahead and I linearize that map. So I now get a linear disturbance mapping, mapping pink arrows onto green arrows, expressed here by this matrix J. And what I do with this matrix is I go and look for eigenvectors. An eigenvector of this matrix basically means that I found a disturbance that maintains the same direction and only changes in scale. So here's an example for an eigenvalue that is smaller than 1. My original pink disturbance ends up being the green disturbance, which points in exactly the same direction, but is a little bit shorter. This would be a stable mode. You can also have unstable modes where my eigenvalue is larger than 1, and you get a motion, the disturbance stays in the same direction, but you get a motion that's unstable because the disturbance grows and grows and grows. Here's a small check. My computer is running slow. Let's see if that gets better over time. Here's a little check. If I go in this direction, what's the associated eigenvalue? Well, it's 0, right? If I go along the flow of my disturbance, I just end up at my x star, and the disturbance completely goes away. So you can do this eigenvalue analysis, and under certain conditions, for example, if you have a system that's energetically conservative, you can show that there always has to exist an eigenvalue of an eigenvector with an eigenvalue of 1. And that's interesting because an eigenvalue of 1 means that, I'm sorry, something's happening with my computer. I hope this gets better. Otherwise, I'll just restart PowerPoint and see if that helps. An eigenvalue of 1 means it's an eigenvector, so the direction doesn't change. And an eigenvalue of 1 means the length doesn't change. And that means you end up essentially at the same point again. So I just found a disturbance that never changes. In other words, I just found another periodic motion. And I can keep doing that, and that's what the numerical continuation does, is I keep exploring my space in the direction of this eigenvector with an eigenvalue of 1, and I can find a whole range, a one-dimensional manifold, solution manifold of periodic orbits. While I do that, I monitor the other eigenvalues, other eigenvectors and associated eigenvalues. And here I see, for example, that I have an eigenvalue that started at being a little bit larger than 1 and ends up being smaller than 1, which means somewhere in between, there is an instance where that eigenvalue is also exactly 1. So at that point, I not only have one direction in which I can find additional gates, but I actually have 2 directions in which I can find additional gates, a so-called bifurcation, and then I can keep exploring my space in this direction as well. So this is what we did. We worked our way along these solution manifolds, and we end up with a tree-like structure. Looks like this, that represents all the gates that we can find in this specific model. And in the graphs that I show you next, I will only show these lines, right? I'm not going to show the orbits. I just show the intersection of the orbits with the Poincaré section in some projection or low-dimensional representation of the state space. This is how it looks, right? This is our tree of all possible motions that we can get from the simple model. You find, for example, hopping along this branch. So this is simple in-place hopping. You find running motions along these branches. You find skipping. Oh, pardon me. Sorry, this was walking over here. Now we have running over here. I have two-legged hopping along this branch. I have galloping that sort of branches out from two-legged hopping. And then over here, we have skipping. And that's it. Those are all the gaits that this model can produce. So it's kind of funny. With a single set of parameters, with a single model, we can generate every gait that you see in nature. Some of them you don't see as frequently as others, but you find all of those in nature and nothing else. Right? That's not evidence, but it sort of strongly hints that these passive motions, these normal modes that are inherent to the mechanical structure of such systems somehow play a role in the selection of gait. Let's look into these results in a little bit more detail to understand where these different gaits come from. And I want to start with very simple running in place or more hopping in place, where this here is my starting point for my search, this little red circle. That's just me standing in place. And then I start to bounce a little and inject more energy. And as I inject more energy, I hop higher and higher and higher, and I move along the branch that you see here. By the way, do you see my mouse pointer? Yeah, okay, good. Just making sure. So that is hopping in place. Now, how do I get from hopping in place to running forward? And essentially what happens is that I have 2 oscillations, 2 frequencies. One is the model hopping up and down. That is a nonlinear motion because it involves an air phase. So the higher you hop, the longer the motion takes. And I have a passive leg swing, right? The legs are also attached to hip springs, so they also perform an oscillation. Here the frequency is fixed because there's no air phase. It's a linear spring, so you basically get a linear oscillator with a fixed frequency. So there are points where that forward or that leg swing frequency is matched with the hopping frequency. And that's where running gaits arise from simple hopping in place. So basically the hopping in place you see before now gets this extra component of leg swing, and that creates a forward motion. And since you can have multiple multiple leg swings during one hopping motion, I think that's how I should explain it, you get multiple of these running gaits. So for example, down here, I get a weird running gait where I jump up once, swing my legs 3 times, and then take the next stride. So this is basically what you see here. Every time a new branch comes out here, every time we find a bifurcation, I'm matching a leg swing frequency to an upward hopping frequency. I can also cut these motions short when I don't do a full leg swing and hit the ground moving backwards, but I could also hit the ground already moving forward. That's why they show up in pairs. So that's one way of matching frequencies. So having multiple leg swings during one vertical bounce. I can do the other way around, where I have multiple vertical bounce with one single leg swing. And this is the branch that ultimately results in walking. And what we see here is a motion that involves 3 vertical bounce on one forward bounce, and then a kind of, one leg swing. And you see that these are ground reaction forces, they change. And ultimately, we end up in what we know as walking, where we have these double hump ground reaction forces. So we now have 2 vertical motions combined with 1 leg swing. And this is what creates the walking motion. So that's one way of thinking about how gaits are created in such a system, that we're matching frequencies of the different oscillatory components in the system, leg swing, vertical motion, and so on and so forth. Another way of thinking about how gaits are created is to think about them in terms of breaking symmetry. Here's another example of hopping in place. This is now the second scenario where we start our simulation with both feet on the ground, making contact at the same time. So again, it's a bouncing in place motion, but now with both legs at once. And what we have here is sort of a nice symmetry. The model is forward-backward symmetric because it's hopping in place. It's also left-right symmetric because the 2 legs are just pointing straight down. And what I can do is that I can break the symmetry. So for example, I find at the right frequency again, I find a branch where I go from hopping in place to hopping forward. So I'm now breaking the forward-backward symmetry, and I create a forward hopping motion. And because I break symmetry, there has to be equal or equivalent backward hopping motion that you see here, right? So there's actually 2 branches coming out of this, breaking this forward-backward symmetry. And then I can keep going ahead and keep breaking symmetries. Now I can break the symmetry between left and right, which means the 2 legs, left and right, are not moving together anymore, but they are hitting the ground in sequence, either left foot first, then the right foot, or right foot first, then the left foot, giving me these 2 different galloping branches. So that's another way of intuitively understanding of what's happening with this model. What do we get? Well, there's this nice finding, not true evidence, but at least pointing in the direction that these modes, these non-smooth, nonlinear normal modes, are important in locomotion and nature, that they are maybe something useful in robotics. But then the question is, how do you use this, right? How do I take these results and make them useful for a roboticist, basically use them as a blueprint to generate gaits for robots? And this is work that's not completely done, so it's not published. It's still a little bit work in progress, but I think it's pretty exciting, and that's why I wanted to share it with you. And it starts with a idea that actually passive is the optimal active. What do you mean with this? Well, if I look at our little model here, I can go ahead and use the methods that I just described there, which are basically just numerical optimization, numerical continuation approaches to find all gaits that this little system can exert. So here's a branch with 2 walking gaits. Pardon me. Shown here, I was hoping that there's some animations, but they don't show up. So here's your walking branch. And then we say, well, this is a passive model, but what we can do is we can add torques. We can put actuators in here. Now, it's not a passive model anymore. It's an active driven model, but it still doesn't have any losses. So in a sense, what we have now is, I don't know, something I would call a non-dissipative model. So it doesn't lose energy, but there are actuators, so we can play with it. And we can use these actuators to apply torques. And we get these torques from some sort of controller. Here's a very, very simple controller that applies negative damping to the joints with some damping constants psi. The reality is a little bit more complicated because you don't want to apply torques, for example, when your feet are in the air. But sort of roughly speaking, what we have here is negative damping with these parameters psi. And now that sort of extends the space in which I have to consider my systems. Since it's not only passive, I don't only have to look at the states and monitor those, but I also have to consider my actions expressed through these controller parameters psi. And associated with these actions, I will get some cost, right? Doing actuation will inevitably create some cost. So here we have our damping parameter, or one of them. Here we have one state, forward velocity, and we have a cost function, which is just torque squared. When I have an actuator, I can pick different psi here, create different actuators, and create more motions than I originally had, but they all will cost something, right? So by adding or increasing by negative damping, I can create motions that I didn't have before, but because I use actuation, they will actually cost me something. And my original passive trajectory is still going to be the globally optimal choice, put it this way, with a cost of 0, right? If you don't do anything, you're not gonna assign any cost, right? And so we still have these passive motions that we identify, but at this point, we just think of them differently. They're not passive modes, they're actually optimal motions of an active, but still non-dissipative model. That is cool, right? I just created an optimal gait, and not any gait. I actually created a globally optimal gait because it has a cost of 0. And I have a method to find all of them through numerical continuation of these nonlinear normal modes. Now, of course, the question is, this is for my silly this non-dissipative model, and I want to control a real robot. So there's still something I need to do. And the idea here is that we use homotopic models that can basically be morphed from one into another. So here's the idea. I have my very simple active but non-dissipative model on the left, and I somehow want to relate it with a realistic robot model shown here on the right. And you already see that I introduced a lot of parameters here that I then set to 0, parameters that show up over here. And basically, that already highlights the idea. What I want to do is I want to introduce a parameter that lets me seamlessly morph from this model to this model. In order to do that, I need to add a few more things, right? I have to make this model, add dissipation to this model, make sure that structurally this model and this model are the same. And then I introduce a parameter that if I set it to 0, I get this model. If I set it to 1, I get this model. that's done very easily. So for example, I have here a torso distance dt, and here I would set my torso distance simply to epsilon times dt. I have a foot mass here. I would set the same foot mass here to epsilon times whatever that foot mass is. And so I can parametrically scale this complex model into my very simple passive representation that I can use to identify my passive gaits. And then, of course, I can go the other direction and slowly go from sort of epsilon 0 to epsilon 1, again doing a numerical continuation, this time in epsilon, so in codimension 2. And as I do this numerical continuation, I trace my optimal gait. So I trace this minimum. I know I start in a minimum because I have a cost of 0, and I just keep tracing these first order optimality conditions that are associated with this minimum to end up with this model. This is how it looks in animations. So here's my passive model, epsilon equals 0. And then I slowly change my epsilon, morph the model, get to something that is halfway between a passive model and a real robot. And I keep doing this, and I end up with this optimal motion for an actual robot model, something that you could build that was grown out of my passive normal mode. None of this is published yet. We still need to sort of understand a little bit better the theory behind it, write it all up, create maybe a little nicer use cases for it, but that's the basic idea. I guess I still have a few minutes, and I want to add an epilogue to this talk, which is sort of that's a fun part. And it's a bit of behind the scenes story, and it's also a bit of a shout out to one of you. And the epilogue is called "None of This Should Work." So everything I just showed you should not work in theory. At least we think it should not work in theory. We're not entirely sure. It does work in practice, but theoretically it should not work. Here's the reason why, and it has to do with contact. Contact in mechanical systems. And contact in mechanical systems can be tricky. Here's an example. I have a dumbbell that is falling onto a floor that has some compliance and 0 friction. So I call this soft ice. No smiles. Come on, soft ice. It's late here. That's my apology. And if I run a simulation, you kind of see that it hits the ground, it penetrates the ground a bit. First on the left side, then on the right side, ends up somewhere up here. This is how contact works. It's always physically some elastic interaction. Typically, not as soft as it's shown here, but you usually have something that is a lot stiffer, like the interaction between the floor I'm standing on and my feet is much, much stiffer than this, but that's sort of the general principle. What's also important to note here is that the result that I get, which is basically this thing here spinning counterclockwise at the end, is mostly a result from the sequence of contact. So I hit the ground on the left first, which introduced a clockwise spinning, which means that my second collision here is much stronger. And that gives me sort of then this counterclockwise spin. Since in reality, things are much stiffer, we typically try to get systems that are simulated or simulates systems that have much stiffer contact. This is what you've seen here, just going through powers of 10 in terms of stiffness. And what's kind of interesting is as long as these two contacts are clearly separated, if they happen one after the other, we more or less get the same results. You can actually analytically show that the stiffness doesn't really change the outcome of the collision process. Of course, I get deeper penetration. I need more time during contact. But all of that, I get larger forces, but all of that can be normalized and taken out of the picture, and you essentially end up with one single solution independent of stiffness. And in the legged robotics community and in mechanics in general, people take advantage of that because you don't want to simulate the physically unrealistic, very soft system. You also don't want to simulate a physically realistic, very stiff system, because that's numerically expensive, gives you stiff differential equations. So what we do is we approximate contact as being completely rigid. And in the limit, there's no difference between very, very stiff and infinitely stiff or completely rigid. So that works well, as long as you have single contact. Different story if you have double contact. So here I threw my dumbbell at a slightly shallower angle, and now I hit the ground with sort of both sides at once. Not completely simultaneously, but there's some overlap. And during that overlap time, the two effects cancel each other. And that means that I don't get sort of this bounce left, bounce right effect that I saw before. But well, these two effects cancel each other. The problem is, if I now do the same thing I did before and I start increasing my stiffness, I get different results. Every time I do this, I end up with a different terminal rotational velocity, because that duration of overlap depends on the stiffness. If I get stiffer and stiffer, at some point, I'm so stiff that, again, my two contacts happen in sequence, and I end up with a different solution, as you see here, than I would get with a very soft system. Now you can say, oh, don't worry, that's no problem, because I can make my system always so stiff that my contacts happen in sequence, at least from the perspective of my collision computation. The problem is there is this corner case of hitting the ground completely simultaneously. And here you see 3 simulations running at the same time with slightly different initial angles, slightly turned to the left, 0, slightly turned to the right. And you see that for low stiffnesses, I have to show this video again. For low stiffnesses, I see no influence of the order of contacts. I just bounce off with no rotational velocity. And then after a certain stiffness value, I get this very, very large sensitivity with regard to my initial conditions. And that's essentially the problem that I'm talking about, that stiff systems are very, very sensitive to initial conditions because the outcome of the simulation depends on the order of contacts. So discontinuities arise in the limit for rigid contact. Here's a graph, initial angle, final angular velocity, and you see sort of these zones where this is contact happen in sequence, contact happen in sequence. In between, there's sort of this mix for very soft contact, and then for stiffer contacts, that intermediate zone gets shorter, shorter and shorter, and I end up essentially in the limit with something that is completely discontinuous. If I hit the ground left contact first, I end up with this velocity. If I hit the ground simultaneously, I end up with no rotation. And if I do it in the other order, I get a rotation in the other direction. Okay, why does that matter? It matters because in our process, we use derivatives, right? I glanced through this like here, you do your disturbance, you get your map, yada, 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 you linearize your map. So I take a derivative here, which only works if, well, if the system is differentiable, and the system I just showed you was not even continuous. So the big question is, in this context, is do I even exist, right? And that's something that is actually pretty well known for hybrid dynamic systems. And people typically don't care because they say, well, this problem only occurs in this instance of double contact. And double contact is, you know, it's a bit of a singularity, an outlier. We just steer away from double contact and we look at trajectories where the contact sequence does not change or is, you know, is kind of a little bit away from this double contact. unfortunately, we can do that because our approach is interested in exactly these bifurcations, where you go, for example, from hopping, where you have this double contact, to galloping, where that double contact vanishes. So in a sense, I'm actually driving my search actively to these corner cases, right, that everyone wants to avoid. And in order to detect this bifurcation, I don't only have to be continuous in terms of my dynamics, I also have to be differentiable with respect to my dynamics. Now, we were totally unaware of this when we did this. So we didn't think about it. We just did on derivatives numerically, and it seems to work. But after a while, we started thinking about it, and we realized this shouldn't work. And it's kind of stupid because I actually saw this coming. Like 10 years ago, I did a study where I looked at a passive dynamic quadruped, where you have exactly, when you look at trotting gaits here on the right, you exactly have this problem because the 2 feet strike the ground at the same time, and you actually find 3 different gaits, 1 exact gait, 2 inexact gaits that corresponds to being exactly on this corner case of hitting the ground simultaneously and being a little bit away from it. So the idea is basically when both feet move forward and I get this contact, I can compute it in this order, I can compute it in the other order, or I can do both at once. And then you stack matrices in front of each other. It's all linear, but these matrices don't commutate. So you end up with different results, and you end up with gaits that are singular. So there's sort of, here's your exact 2-beat gait, and then this would be another periodic solution. This would be another periodic solution. This is a sketch of the Poincaré map. So that is a problem. Well, maybe it is a problem because for some systems, you can get around this. So certain systems don't suffer from this effect. In this case of our simple dumbbell, that happens if I make the mass of this connecting rod here 0, and essentially I have 2 point masses. What this does is that the contact between these two is decoupled. It basically means if I have my contact on the left side, the left mass bounces up, but the velocity on the right side does not change. Before, the velocity here changed, but also the velocity here changed, which then basically created this effect of the rotation afterwards. Here, that does not happen. So the 2 contacts are completely separated, independent, and I don't see the same effect. So independent of my stiffness, I get the same result. I don't see these discontinuities as I go through this singularity of having double contact. For our system, that's true. So the inertial coupling is decoupled. Our de Lacy matrix is diagonal. All that works, but it's not necessarily differentiable. So that's the next thing, right? Continuity is just one thing, but you also want to be able to create derivatives. And they should be the same on the left and the right because you want to do bifurcation analysis. And that's what we need for that, right? So here's the part of the story, right? So we discovered this effect 10 years ago, and I just considered it as not important. It was kind of, yeah, it was funny. I reported it in this paper, but never thought about it. And then other people were a little bit more visionary and essentially picked up on this idea and tried to create rules for models, how you have to build your model so that you get a system that's differentiable. And when Sam told me about this, I actually first thought, I have to be honest, I thought, oh, this is cute, right? This is mathematically interesting, but who will ever need that? This is such a theoretical topic, right? Yes, it's interesting, but why just stay away from these double contacts and you're good. So we're reading your paper. I think that's what I'm saying. We're working through your paper and trying to incorporate it in our work and make it work for us. That's it. I never ask how much time I have, but this seems reasonable. I stop here. Thank you very much. And please, if you have any questions, don't yell. Raise your hand, and then Sam will unmute you, and then yell.
Perfect. Thanks so much, David. That was fantastically interesting. There was one question on the chat I'll read, but for other folks, you're welcome to put questions in the chat, or if you do a little Zoom emote, like David said, I have the power to unmute you so that I can unmute and call. So go ahead and think of your questions and raise your hands or put up your smiley faces or things like that. So David, a question that came earlier on in the talk, but I thought it, oh, okay, well, so Daniel said that the question was answered in the talk, which is partly my suspicion, but I have kind of a related question, because the original question was, what do these different modes represent, and what does it mean to transition between them? And so my question is, because you kind of addressed, these different modes correspond to these different possible behaviors for the robots. In the same way that you can do this continuation from, a more simplified or reduced order model to a more detailed model of the robot to get a gait to embed, is there any notion of using the continuation between the gaits to do like gait transitions, like controlling the robot to do gait transitions?
It's interesting. I always get this question. That's good. That means it's a valid question, and maybe I should start addressing this. But if you look at this graph, right? I think a big misconception is we see gaits and they are connected, and then people automatically think, oh, that's a gait transition, right? And gait transition is me, walking down the street, realizing that the bus is turning the corner and starting to run, right? That's a gait transition, which would be going from walking to running. And of course, we have active systems, so we can go anywhere within the space we want, right? If you have actuators, you can move in this world of trajectories wherever you want, within limits, right? But I mean, if you can run and if you can walk, you can definitely jump from one to the other. So that's sort of the gait transition that I would think of in daily life. What we see here are transition between gaits that are not so much points where you should move from one gait to another, but points where two gaits are the same. So maybe if you move along this galloping arc here, there comes a point where sort of your galloping changes to a point where the 2 feet move together in unison, right? So if you move along this branch, you have a large split between the legs, and then that gets smaller, smaller, smaller as you move along the branch. And here they're exactly the same, actually, and then the branch continues on the other side with the split being the other leg being ahead. So it's more that at this point, hopping and galloping are the same, right? You gallop with 0 phase shift between your legs. Here, in-place hopping and forward hopping are the same because you hop forward with 0 horizontal velocity. So those are the transitions that we see here, right? I don't think that we can get any of the other transitions, even through some other continuation, because I mean, all we do here is we look at periodic motions, right? So maybe there's a way of setting up this problem that you say, I want to have a passive motion that starts at walking and ends at running. So there's sort of a transition motion that we somehow try to find, and then maybe we can grow that. But I don't know how to do that, because in that case, I wouldn't know how to define walking and running, right? We define it as something periodic, and then by definition, you cannot really have the trajectory from one thing that's periodic to another thing that's periodic.
Yeah, fair enough. What other questions do people have? And again, feel free to type into the chat or raise your Zoom hand. Okay, we've got a question here. I just need to find the person and unmute them. Okay, there you go, Joey, you're unmuted. Oh, And now you're muted again.
Sorry, I muted myself.
There we go.
Yeah, awesome talk, Professor Remy. I have a question about these models and how they're used in the numerical continuation. So these models, they don't have any dissipation and there's no actuation. And so it seems like if I was trying to do this numerical continuation, I would take some point in my Poincaré section and I want to simulate it and see where it comes back, that when you perturb it, that it wouldn't be stable. So I guess this is a technical point. Like, are there things about these models that are passively stable that allow you to do this? Or is there something that you have to do to make sure that just this numerical continuation is like stable?
Okay, so that's a really good question. Thank you. And I think there's a two-part answer. The first is none of this is stable. Like if you do a true stability analysis of these motions, they are all unstable or highly unstable. Like if you disturb them a little bit from the periodic motions you see here, they will spiral out of control quickly. But there's always an eigenvalue of 1, sort of this metastability, which basically means there is a neighboring solution. And the reasoning why there has to be one is actually very simple for a conservative system. If I have a conservative system, I preserve energy. So the energy at the beginning of my stride and the energy at the end of my stride is the same. Energy is a function of state. So this constraint on energy is essentially a constraint on my state, which basically means that if I have n-1 states that are periodic, with this constraint, the last state also has to be periodic, right? If n-1 states map onto themselves and the energy remains the same, then this last state cannot be different, because then I would have a different amount of energy. So my periodicity constraint is actually only of dimension n-1, whereas the number of variables I have are my states, right? That's of dimension n. So I'm basically trying to solve a non-square problem here, where I have energy as a free parameter. And these curves here are actually, or can be interpreted as functions of energy, right? Most easily visualized here, right? This is the hopping in place branch, where you start as just standing still and then you bounce a little, and as you move along the branch, you inject more and more energy. And I sort of know that these one-dimensional solution manifolds have to exist. The numerical implementation is a little bit more involved, because what we actually do is that even in the passive model, we introduce a little bit of actuation, an actuation parameter that we know has to be 0, but that basically allows us to compensate for any numerical losses that we have in the system. So we don't actually assume that we have a conservative system, but we have a system that we want to make conservative. And because we add this additional variable, it's like a global negative damping parameter, we add a constraint on energy level. And so what we want to get is essentially a set of square solutions that is explicitly parameterized by, a set of squared equations, or n equations for n unknowns, that is explicitly parameterized by energy. And then for conservative systems, of course, this input parameter, it's essentially a Lagrange multiplier that we introduce here, is typically 0 or very, very close to 0. Right? So there's a little bit of craftsmanship behind that, because otherwise you assume the system is conservative. You run you're trying to find something periodic, and because you have numerical damping and other effects in there, you can't find it. Right? That's the other side of this energy equality. If you somehow lose energy along the way, you'll never find a periodic solution.
Okay, great. Any other questions people want to ask before we sign off here? selfishly, I get to meet with David one-on-one as soon as this session ends. I have a lot more questions, but I'd like to take mine offline. So if anybody has any other questions they'd like to ask, please feel free to interject. All right, then I'm going to suggest that we adjourn. We thank David again for giving us such a wonderful presentation. We can go ahead and stop the recording. And
yeah, thank you. Thanks for having me. Happy Thanksgiving.
thanks very much.
Thank you.